In the previous lesson, we looked at what we do when we're given that lines are parallel and the conclusions that we can reach from it. So in this lesson, we're going to look at how we prove that lines are parallel. So instead of being given parallel lines, we're going to be asked to prove that lines are parallel. So let's review some ideas here. Here I have 4 angles at this vertex, and we know that the vertical angles here are congruent. So if this has measure x, then this also has measure x. And if this has measure y, this also has measure y. And we also know that any of these adjacent pairs of angles have to add up to 180 degrees, that they are supplementary. And we learned that if these lines are parallel, then these 4 angle measures copy down to here. As it turns out, the reverse, or perhaps to be more precise, the converse, is also true. If I know any of these 4 angles is copied down to here in the corresponding place, for example, if I know this is a 1 tick marked angle like this one, then that tells me that these lines must be parallel. And there are 3 common configurations that you should learn to recognize for proving lines parallel. One is this shape right here. It looks a little bit like an F. These are corresponding angles. And we can say if corresponding angles are congruent, then we can deduce the traversed lines are parallel. In this case would be L and M that are parallel. The second common configuration is if we have alternate interior angles. For example, if I know this angle here is congruent to this one, there's that Z shape we spoke about in the last lesson. Those are alternate interior angles. And alternate interior angles congruent also implies that the traversed lines are parallel. And finally, one that we will see more in a future lesson, but not so much in this one, is if we have same side interior angles. That would be this X and this Y. If those are supplementary, then these traversed lines must be parallel. So same side interior angles supplementary, meaning they add to 180 degrees, also implies that these lines are parallel. So here are 3 common ways to show that lines are parallel. Here the shape of corresponding angles is sort of like an F. It would be these angles. Alternate interior angles looks a bit like a Z or an N, like this. And then same side interior angles looks like a C or a U shape. Here we need these angles to be not congruent but supplementary. So here's a couple of algebraic problems testing these ideas and demonstrating them. First of all, I made a note here. You must keep straight when you know lines are parallel and when you need to prove lines are parallel. And it's clearly stated in the problems whether you know that lines are parallel, whether you prove that lines are parallel. Here's an example where you know lines are parallel. Here's the question. If L is parallel to M, that's like a given. So we know these are parallel. I'll put some little arrows here as a reminder. If L is parallel to M and we know all this information, what is the measure of angle 3? So here we have angle 1, angle 2, angle 3, and I have these measurements for these. Don't be thrown off by this little M in front of the angle here. When you see an M in front of an angle, this is read measure of angle 1, and it's just simply a way of saying how many degrees it is. Sometimes I'll put it in there, sometimes I will leave it out. It's just measure of these angles. So let's label this information in this picture. We know that this is 3x plus 20, or minus 20 degrees. And we know that this angle is 2x degrees. And we know that these lines are parallel. Well, if I look at the configuration of angles here, since these lines are parallel, I know 1 will copy onto 3. So if I could figure out what angle 1 is, I'll know angle 3. I know angle 1 is this, but I want to know the value of x first. But if 1 and 3 are the same, that means 2 and 3, well, we know 2 and 3 are supplementary. So if 1 and 3 are the same, that means 1 and 2 are supplementary. And we saw this in the previous lesson. These are same side interior angles. and same side interior angles are supplementary if these lines are parallel, which they are. So I can say, because these are supplementary, so I can say angle 1, angle 2 are supplementary. So 3x minus 20 plus 2x has to equal 180. And this is a straightforward little algebra question. I have 5x minus 20 is 180. So 5x is 200. Dividing both sides by 5 means x is 40. That's not my answer though. The question is, what's the measure of angle 3? And as we mentioned earlier, since these lines are parallel, those are the same. So whatever angle 1 is, that's what angle 3 is. Angle 3 is congruent to angle 1. So angle 3 is 3 times 40 minus 20 degrees, or what is that, 100 degrees. Using the fact that angle 3 is the same as angle 1 up here. So this is an example of what you can do when the lines are given parallel. I was set up equations relating an angle at one vertex and an angle at another. Here's a second example. Now, we don't know that lines are parallel. I made some alterations to this so you can ignore some of these marks here. In this diagram, then I give you all this information. Then I ask, is L parallel to M? Explain in a sentence. So now we don't know if L and M are parallel. We're asked to determine whether they are parallel or not. So I have 1 and 3, and once again 1 and 3 are same side interior angles. But because I don't know if L and M are parallel or not, I should not set up an equation relating things at one vertex to things at the other. I don't know if the lines are parallel, which means any equation that relates angles at this vertex to angles at this vertex is speculative and is a bad idea. What I do know is that these are vertical angles. And irregardless of whether these lines are parallel or not, these angles have to be congruent, which means I can set their measures equal to each other. So that's what I'll do, and we'll see what we get for these measures of these angles. Since angle 1 and angle 2 are vertical, I can say 6x plus 15, angle 1, is 8x minus 9, angle 2. So let me solve this equation. I'll subtract 6x from both sides. I'll add 9. Dividing both sides by 2 gives me x is 12. So, what are these angle measures then? So angle 1 was 6x plus 15. So that's 72, what is that, 6 times 12, 72 plus 15, that's 87 degrees. Angle 3, 7 times 12, remember x is 12, we figured that out here, plus 2. And that's 84 plus 2, which is 86. So what does that tell us? Well, remember, if these lines are parallel, then these have to be supplementary. These are same sides interior angles. Since angle 1 plus angle 3, which is 87 plus 86, is not 180, the same side interior angles are not supplementary. So L is not parallel to M. Let's look at these ideas in a proof. So here's a proof where we have to prove lines are parallel. We're given BC is congruent to AD and BC is parallel to AD. We want to prove these lines parallel. So this is the new thing. We haven't done this before. So let's mark our givens. They're congruent. and these are also parallel. I use my little arrows here next to them to show parallels. So, sorry about that. Continuing. We want to prove that these lines are parallel. So, I don't have any triangles here. So what I'm going to do is I'm going to make triangles. I've seen this diagram a lot before, and I know that putting in a diagonal one way or the other is often helpful. I'll put one in this way. It would also work to put it in the other way. I suspect that these triangles are going to be congruent, and I can hopefully use that to show that these lines are parallel. In order to show that these lines are parallel, I need to show that they have congruent alternate interior angles or congruent corresponding angles. I'm looking for Z or F shapes that involve these two parallels. And I've just created one here like this. There's my Z. So if I can figure out that these angles are congruent, that will tell me that these lines must be parallel. That's the logic. The previous lesson, we knew things were parallel, and that told us certain angles were congruent. And now we're turning it around, and we're going to say because these angles are congruent, therefore these lines are going to be parallel. But first I need to prove these triangles are congruent. So let's think here. I have this sides marked already, and here's the shared side. So there's side, side. And then I have these given parallels right here, BC and AD. And here's another Z. There's two Z's in this diagram. In this Z, we know these are parallel. This is a crucial distinction. Since we know these are parallel, it's a given, I may immediately conclude that these Z angles, these alternate interior angles right here and right here, must be congruent. I can't say the same of these from these being parallel. That's part of a different Z. So what do I have marked here? I have side angle side, and the other triangle has side angle side. So therefore I have these triangles are congruent. I'm going to say triangle ADB is congruent to triangle CBD. I'm going to be using side angle side. One pair of sides is the givens. BC congruent to AD. The other pair of sides is the shared side in the middle. BD is the side of both triangles. So that's the same side. And then my angles in my SAS came from knowing that these were parallel. So this is angle CBD and angle ADB. And they are congruent because they are alternate interior angles. But remember, I can't say that unless I know that these lines are parallel, which I do. That is a given. So there we go. I have my congruent triangles. So remember, my goal here is to get these other lines parallel. So I'm going to use these Z angles. So now I'm going to reverse this logic. This logic here works both ways. Here I know that the lines are parallel, and I deduce that these angles have to be the same. Now I'm going to reverse it. I know that these dotted angles are congruent because of the congruent triangles. So those dotted angles are angle ABD and angle CDB, because they're corresponding parts. And then reversing this logic exactly, I'm going to do it the opposite way. Because these Z angles, because these alternate interior angles are congruent, that tells me these lines must be parallel. And so I can conclude AB must be parallel to CD. And for the reason below, I'll just say I have congruent alternate interior angles. If the alternate interior angles are congruent for these two lines, then they must be parallel.